I don't think it was, yeah. Anyway, sorry. So let me just write that there are two posets. Okay, there are two posets, and there is a function f like this, and there is a function g like this. F and g are order reversing, so I will just write f and g are order reversing. But the main property which we want to write, okay, is this that S is less than or equal to G of f of S. Okay, so I'm asking the same question again. Do you see? I'm not writing S and T in the subscripts because we understand. Okay. Do you see what this is an example of? What does it abstract? Which property of fields and groups studied in this chapter is this an abstraction of? So where have you seen this? Right? So let me just say, so you just take a K and F, which was just same thing. You take L. This is your S, right? Now, oh, okay, wait, what happened? Sorry, yeah. Now you go from L to gal uh, K over L, right? I mean, this you can always do. You don't even need a Galois extension. Gal K over L just means automorphisms of K which fix L, and nothing more than that, right? So this, and this is basically your Fs. And then when you take your fixed field, the F is your, this capital F, the fixed field function is your function G basically. And we all know, we have studied this in the chapter, that this is true. And this is also an obvious statement. What is the field fixed by these automorphisms? They are fixing L by definition, so they will at least fix L, right? They will at least fix L. So that's why it's greater than equal to. In fact, it will be equal to if it's a Galois extension. And if and only if it's a Galois extension. If and only if, yeah, I mean, certainly if it's a Galois extension, it will be fixed. Yeah, but anyways, for Galois extension, you need it, something. Well, let's not get into that. But is it clear, right? What this is saying? Okay. So similarly, we have the other property. So these are the properties, and let's just let me just see the same thing, but let me just see it to be sure. Right. So there is the other property, obviously, where the t is less than f of g of t. Okay. So I will just write such that, and can we just see this in the same example? That is the question. So let's see. So you have gal k over f. Maybe I should not have erased it. Gal k over f, and then you just take a subgroup H. At this point, we don't know if the subgroup. Let's say we don't know if the subgroup looks like gal k over L. So we just take a subgroup, okay, and now you take the fixed field of H, right? This is basically your G, right? And now your uh, f of this, so what is this going to be? This is going to be the automorphisms of K which fix FH, right? By definition, F takes any subfield, in this case FH, and it gives you the automorphisms which fix it. I mean, they might be fixing more things, but they should at least fix FH. That's the point. So, does this contain H? Right. So, if you take anything in H, yeah, I think this is true, right? Yeah, this is like, again, by definition, isn't it? Yeah. So, did they say it's 1, 1? Suppose that these are functions. Prove that there is a 1, 1 order reverse. Okay, yeah, that's fine. This is obvious. Hmm? S is uh oh, wait, wait. So you're solving the problem, right? Yes, yes, yes. So just before that, so this statement is obvious. Okay, so let me just erase that, right? So that was just an example. Yes. Wait, now let's just me just state the question. Means just to formally. So yeah, so we need to show that there, yeah, because after that there is really nothing to show. It's just that theory, but still there is a, I mean, it's easy. That's what I'm saying. There is a 1, 1 uh, order reversing, obviously, by 1, 1 order reversing bijection. So it is a bijection between what? It's not a bijection between S and T. Okay, that is to be noted. Otherwise, every extension would be Galois, right? So it's not a bijection between S and T. Bijection between image F and image G. Okay, and as Aryan was suggesting, basically what you do, you just take something in the image. So you take f of s. So you take something in the image. Maybe I'll write it this side, right? F of s, and then you send it to g of f of s, and then again when you send it to f of g of f of s, then you just show that it is equal, which is just following from these two things. Is it fine? It just follows directly, and that's what you were suggesting. That is what it is, right? Yeah, it's the same thing. Everything is symmetric with respect to f and g. Yeah, yeah, exactly right. So it's important to just notice that the bijection is only on this subsets. It's not on the whole thing. Okay, so this is really important. So basically, the good thing about these relation is that when you apply them like more than two times, and they end up becoming like fixed, right? I'll just write this one thing once again, right? This is equal to f of s, right? And why is this? Because we know that, I mean, I'm just sort of doing the same thing again. Maybe this, we know this, and so we know the other way. I just wanted to see it. So we know this, and how do we show the other way? How to show this? Yeah, that is just from the property 2, from this property, right? That this is, I mean, that's just by just put t equal to fs, second property. So both these things are true, and hence this is true. Okay. So this kind of partial order is called a Galois connection. It's a deep thing. So I mean, it's very simple, but Galois deep in the sense that it's a pervasive thing. You can find it everywhere in mathematics. Okay, I'll maybe give you one example. Yeah, maybe on the next page, just giving you. And this you should just try it yourself, and mostly you can do it, but otherwise you can discuss. So maybe I'll just write example of a Galois connection, right? So, yeah, let's stick with, okay, yeah, let me just do it in general. So you take this. This is just, sorry, this. This is just a set. And what is this? This is, it's called the affine K space. And you may know this from geometry or whatnot. So this is just, write it, yeah, like this, where xi is in K. It is just this set to begin with. And the other thing that I would like to write is this, where this is just ideals. Okay, no, so that's not what I wanted to write. Sorry. Is this polynomial ring in n variables. So these two things are there. Now I'll just like you had fields and groups. Now here we will take subsets, which are, well, I eventually want to take, but yeah, fine. In this case, it's a bit special. Subs, yeah, subsets which are zeros of some family of polynomials, common zeros, which are common. Yes, yeah. So this is a very simple version of that. Yeah, mostly. this is probably the simplest setting in which you can say this, yeah. Subsets which are, then it's fine. Subsets which are common zeros are family of polynomials. Yeah. So basically, so since you have seen that, and I suppose Eugenie, you would have also seen this, like just subsets which are zeros of maybe in commutative algebra or something. But I'll just formally still just write it. Maybe I don't need to put that circle. Yeah. And but I'll just mention what the correspondence is. And here we just have ideals. Okay. Uh, yeah, I should be writing something. Okay, maybe I can write it. Why not? Radical ideals. You can look up the definition if you don't, if you have not studied commutative algebra. But if you have, then you. But otherwise, you can just think of ideals. Actually, it's fine. For purposes of Galois connections, it's sufficient to consider ideals actually. So let me just write ideals and and ask you to identify ask you to identify, right. So in that case, actually, I'm sorry, but I'll just change this, okay? And I will ask you to identify the images on which the bijection holds. So this is going to be just subsets. Okay. So now there is a very obvious f and g, very natural f and g. What is it? So this f of a subset here, let's just call V. This is just obviously going to be f, sorry, this is just going to be a collection of polynomials P such that P of V is equal to 0, right? And this is going to be an ideal and so on. And then you look at G of an ideal. This is just going to be the points. So I'll just write like X such that uh, P of X is equal to 0 for all P in I. Okay, so you're going to get this. Now show that this is a Galois connection. Okay, please write this. It's very important. So you have the subset. So you have a inclusion. You have here also you have by inclusion. So you have partial order. You have a map. Check the properties of Galois connections. Okay, there's actually a series of exercises in any algebra geometry book in the beginning, but they don't use the language of Galois connection usually. They will just ask you to solve them explicitly. Okay, right. Exactly that order, because you can understand that will the order which will do it. I've even given you the maps. So now you decide number one. Then you decide the images, right? What are the images? Important to identify the images. On what image? Um, on what image sets is the bijection going to hold? Okay, bijection going to hold. So yeah, so check that this is the Galois connection. Check that. Right. Okay. Then the deep fact in this theory, just like there is a deep fact in Galois theory also. So can you tell me what is the deep fact in Galois theory here? Yeah, I mean, Galois connection is just an abstract thing, right? But the deep fact is that if S is if S, which we took to be a field extension and then subfields, if that original, the mother field extension, if that is a Galois extension, then what can we say? That it's in fact bijection. Image of F is equal to T and image of G is equal to S. That is a deep fact. That is something which is not obvious. Is it? Am I right? That is something which is not obvious, right? And that is what you have to go through Galois theory to understand that. It's something natural, something which should happen. It's good that if it happens, but it's not natural. It's not obvious that it happens. Take a few examples and maybe it works. Here, what is the deep fact? Here, the deep fact is Nullstellensatz, right? So here, if you look at Hilbert's, so of course Hilbert has three like very famous theorems, and one of them is Nullstellensatz, which maybe we can, if you solve this exercise, then maybe next time we can discuss. Okay, Nullstellensatz, and there the deep fact is that obviously all subsets cannot be the answer. That's not going to happen. But if you okay, then what is the problem? So obviously all subsets is not going to work. But if you just take the image of these, yeah, you take, yeah, right, you take ideals and you take the images, there of course you will get certain subsets. Those subsets are which I wrote in the beginning. They are zero sets of common zero sets of polynomials, collection of polynomials. You take those subsets. Okay. So so that's the image of G. You have already identified it. By definition, you have defined it and you identified it. But what's on the other side? What is the uh, thing that what is a sub? All of them will not give you a bijection, right? So here on this side, what you will get is what are called radical ideals, okay? Which I'm not going to say right now. So now if you restrict to radical ideals, and on this side, if you restrict to closed subsets, yeah, but then there is some problem. Yeah, so if you restrict here to, so those are called closed subsets. And here if you restrict to radical ideals, then this exercise will tell you that they are in bijection, right? This exercise will tell you that they are in bijection, but then then we have already proved Nullstellensatz. So I suppose the solving this exercise might be difficult because here you will need K to be algebraically closed, otherwise it is not true. Anyway, so you think about it, you try to solve this and see. Because I know that this result is true when algebraically K is algebraically closed, and it's not true if K is not algebraically closed. But yeah, but think then probably this part might be difficult. But yeah, think about it. But if you think about it, then we can discuss it next time, right? But you know what you have to try to do next. So that's clear. So yeah, and then there are other places where Galois connections come, but but yeah, we'll talk about it later. Okay? If you do this, then we can take another example next time. Okay. So 13, 14, 15, we have mostly done. So let's not do it. Yeah, these are, yeah, let's actually do this. Problem number 17. Yeah. Okay. So I'll write this question. Okay. Yeah. This is problem 17. So for this problem, K FP and The extension is kx over k. Okay. Since we already know what is kx, so let me not write it. Let me mention the function. So this is an automorphism. Okay, where oh right, so x goes to x plus 1. So is it clear what this means? Right? It would just mean that fx goes to f of x plus 1. So the automorphism is generated um, by what happens to x. This is what you will get. Show phi has a finite order. So phi is means when you compose it, it has finite order. But we can also formally say it by saying phi has a finite order in a group. Then it's nice to say of think of order. So this is easy, right? Phi definitely because phi composed. So here when we say order, we of course mean under composition. So phi composed P is equal to the identity. That's the identity, that's the zero of the group. Okay. And then order is P. Right. So this implies order of phi. But the main question is find a U so that Ku is the fixed field of phi. Determine the minimal polynomial over Ku of x and find all the roots of this minimal polynomial. Right. So you see, we need to look at fixed field, right? We need to look at the fixed field. Just to make some space, I'll erase these things. So phi to the P is identity. So what's the fixed field of phi? So it's a subfield of kx, but what is it? That is the question. So we have done this kind of question, but here we have a characteristic P. So any guesses what the fixed field can be, or any examples in the fixed field? So you see here you have to think in like think in concepts of what you've seen earlier, this kind of thing. So right, that's yeah. Let me just write that. Good. So it's characteristic P phenomena. So if you translate, yeah, this is there. This is there in the fixed field. But that's right. There's certainly is there some more canonical element in the fixed field? I mean, this is vague question, but you know, right? Basically, I'm just thinking about Fermat's little theorem, right? Which says that. So I mean, uh, like so you know this, but these are like as functions. As polynomials, they are obviously different. Polynomials, they are obviously different. But I mean, if we just look at this, is this in the fixed field? Yes, it is, right? Yeah. So you just translate it, do binomial expansion, and then it is in the fixed field. I was not able to should be able to say it from here, right? Can you help me say it from the Fermat's theorem? Well, yeah. So you see, this is I mean, this is not equal in FPX, but of course, if you look at the other version, then you can certainly say that this polynomial is equal to this as polynomial. So think about that difference which I'm sort of stressing upon, that two polynomials being equal as two polynomials being equal as polynomials, and two different polynomials being equal as functions. These kind of things can happen in finite fields. Think about it. Okay, think about two polynomials which are different, but they are same as functions on FP, but they're different as polynomials on FP. I mean, I just wrote an example actually. But think about this is actually a very useful thing in number theory. Okay. But yeah, but this is true. This is same in FPX. Think about what it means for two polynomials to be equal in a polynomial ring. That will help you to actually write a rigorous definition. You can just read the definition, but you can also just write it on your own, actually, the correct definition, if you think up through these examples. So from here, you can see that this will be in the fixed field, right? Because you put x equal to 1 and you will get back the same thing. right? Yeah. So, yeah, anyways, this is true. So let me not. It's fine. So we have one example Aryan has given us, and this is another example. So can we get one example from the other? Is it possible to generate one from the other? Are they the same? I mean, so Wilson's theorem tells us that the last coefficient is same, right? P minus 1 factorial is minus 1 mod P. What about the intermediate ones? Let me write the question properly. Is Px equal to Qx in Fp? Yeah. So since I'm asking the question, I should just make it precise that here, of course, equality means that the coefficients are equal, not as functions. Yeah. Anyways, yeah, not just as functions. This is basically the coefficient, right, of Px or of whatever. This is the coefficient of x to the k, or x to the k plus 1 maybe. Yeah. Yeah, x to the k, otherwise you have to put a product. These are the coefficients, right, of x to the k. If it is 0 mod p, then you are done. Like, for example, you know that if I take I going from 0 to p minus 1, then this is 0 mod p, because we know this. Can anyone just check it through some small example maybe? Here it is true. So that's 0 already checked. Sum of the numbers taken 2 at a time. Thus Uh, 5 consecutive. Uh, uh, right. So what does that prove? Uh, it means that I don't know this. It means that this is 0 mod 5, 0 mod p. Yeah, this is 0 mod 5 for every x. That's fine. But then what? But we want the coefficient of x cubed to be 0. That does it follow? I don't know. Yeah, it is 0. I mean, so yeah, what you're saying is correct. I also feel that how do you prove it? That's my question. Because the last coefficient is not 0. That's minus 1 mod 5, which is also what we want. There should be a nice way to say that these two polynomials are same. And I mean, Aryan, what you're saying is probably like what you're proving basically is that they are same as functions. Yeah, they are same as functions, right? And yes, yes, right. But then, yes. So, yeah, anyways, let's do one thing. Let's uh, solve this problem and then get back to this. Okay, because yeah, because they are a low degree, it might be possible to prove that they are also same as polynomials. Okay, no, let's just do it. Okay, so yeah, if you have this px, I'm sorry, so you have px minus qx. Okay, yeah, so then you have, let's call this gx. Hmm. So yeah, so we have basically proved that g is a zero polynomial. Haven't we? Because we have proved that g has uh, p roots. Number one, 0 to p minus 1, those are the roots. Number two, we also know it's evident that degree of g is less than p because the leading coefficient cancels. This, right, cancels, right? And we know that a polynomial can have at most as many as roots as its degree, unless if it's a zero polynomial. So it implies g is a zero polynomial. So then we are done. Are we making any mistake? So the only thing is about the degree and roots, right? So which is which is true for all fields, right? I mean, if you look at the proof, think about the proof, it doesn't depend on finite field, right? A polynomial of degree n can have at most n roots. This is true for all fields. Yeah, that is fine. Correct. Just go over this. I think these are exciting questions, but just think about all this nonsense. But this is true. Eh, So then we are done. So our examples are same. I say. So it's the degree that really matters here. I mean, I said that two different functions can be the same polynomials, but if they are low degree, then it cannot happen. Okay. Yeah, we could give them examples of higher degree ones, x to the p to the n minus x and so on. But for low degree, it is not possible. So these are the same things. So let me just keep one of them. I mean, I'm just keeping this for more elegance. So I'm just the reason why I'm erasing it, I keep erasing because I think Zoom has a small space. So, but if it's problem, like if you would like to let things be there for some time, then you should tell me. I believe it could be quite unnatural to have things erased. I would find it unnatural at least. It depends on what. But anyway, this is not some theory, so that's why I'm erasing it. But you should tell me. Yeah. So now the claim, and this is where see we have to move forward. The claim is that this is in fact the function field over Qx. Okay. So I'm saying basically all polynomials can be as all elements of the fixed field, right, are basically rational functions of Qx. Okay. Why am I saying this? Because I know fact, and you should know too. And this is important fact, I suppose. It's related to transcendence degree. So subfields of Kx are of the form Kf. I don't know if it is there in that book, but you should think about it. Are of the form Kf for some f in okay. Try to solve this. Okay, I mean you may have to read maybe a little bit here and there, but try to do it. Okay, it's very much related to vector spaces and bases. Okay, so that is the reason why I'm giving you this question. So it means it just comes naturally. So you should, yeah. But otherwise, I mean, without this tool, you will not be able to maybe predict that it should be. It's otherwise it's more interesting how you would predict that this fixed field is generated by a single thing. Okay, but it's similar to that kind of thing that like a subspace cannot have larger rank, even though it can have same rank. Okay, FQ is a subspace, subfield in this case, but it has the same rank in the same sense it's generated by a single thing. Yeah. And one more question which I do not know is maybe we should just write it through an example maybe. Yeah. So even though it's a subfield, is it actually isomorphic? Please think about these things. In general, of course, isomorphic as fields, fixing K, that's our notion of isomorphism. In general, is so basically that kind of question. Is it actually isomorphic? Okay. Yeah, it's not so obvious to me, but maybe if I think I should do it. But since these are not going to be difficult, so please think about it. But yeah, let's try to prove this. So that is also what they say actually. Determine the okay. So first of all, uh, determine the order and find a polynomial u so that ku is the fixed field of phi. Okay. So let's try to prove this. Right, I will leave it, and I think that Aryan's version actually would be easy, would be more help, might be more helpful in proving this. Okay, so this show this. This is not difficult. It's similar to the thing that we were doing last day. I mean, just do it. F of x by g of x equals to f of x plus one by g of x plus one, right? So what this kind of thing means, it maybe you kind of show that f of fx equals to f of x plus one, right? Using those arguments that we did, relatively prime and so on. Then you have fx equals to f of x equals to f of x plus 1, x, whatever. F of x equals f of x plus 1 equals to f of x plus 2 and so on. Using that, you show, I mean, it's clear that if x is a root, then x plus 1 is a root, then x plus 2 is a root, then x plus 3 is a root, and so on, which means that that chunk, which was in Aryan's example, is a root, right? Which basically means that f is a polynomial over that. I mean, f is a polynomial in that, right? It kind of, I mean, you could factor it out, but then the rest of the thing also has that property, right? So you can kind of see what is going on, right? Is that correct? Yeah. So you could try to show basically that a polynomial f this fx would it actually be a function. It would actually be some f1 times this qx, right? If f is in this, and through that you can show at every polynomial. So you don't need this actually this fact, and maybe you should not because this fact is more non-trivial. But I mean, it will help you to predict this. Yeah. So this is fine. But then we know from Galois theory, this we know that kx over f phi. Maybe I'll write this in the next page because uh, this has me. I hope you've noted this. So now we know that kx over k of, let's write it explicitly because we have solved it. This is Galois, right? So if you take any subgroup, take the fixed field, then that extension that we get is Galois. That we know. So maybe I will not say these things, and if you have to ask, then you should ask me. So Galois. And the question is determine the minimal polynomial over ku of x and find all the roots of this minimal polynomial, right? So So find the minimal polynomial of x over. I hope it's not confusing. Think of a polynomial which has x as a root. Now the coefficients are also allowed to vary over x. The example should be the polynomial should be very simple. Okay, shouldn't be anything, should not be anything fancy. Yeah, I would like to write this. This polynomial works, but the problem is that this coefficient is not in this field. So it's not allowed because this works. You just put equal to. So we have to take something. Yeah. Uh, yes. Yeah. Yeah. Right. Good. Yeah. I mean, that's right. This is what I should have said. Nice. That's what it should be. Correct. So as I was saying, but I couldn't do it. So fortunately, but yeah, this is perfect. So you see, we need this, and then it is. This is of course true. There's nothing. Yeah. But I was thinking that we might need one by this in the coefficients, uh, but no, that is a stupid thing which I was thinking. Okay, so this p is in k of. Why is it irreducible? we need to show this, show that. So of course you can show irreducibility by all kinds of things, from Olympiad style or whatever. But from Galois theory, from all this that we know, well, you know that the degree of this extension is p, right? Because the group that it is coming from has size p, right? So the degree of this extension is p. And if the degree of the extension is p, and what is the uh, degree, what should be the degree of the minimal polynomial? That should also be p, right? Because it's clear, I don't need to say anything, but since if I'm saying that, I will just write it properly. So if I call this f, and if I call this k, then k is equal to fx, right? And what is the degree of this? This degree is nothing but the degree of the minimal polynomial. Degree of the minimal polynomial. Minimal polynomial of x over f, whatever. Right? Because it's given by adjoining x. So that it's, and so its degree is d. So we know that the degree of the minimal polynomial is p. So since this already has degree p, so this has to be the minimal polynomial, and so we know minimal polynomial is irreducible, so this is irreducible. So you get that through in this investigation. Now it is not so much about the reason why this is irreducible is not so much related to the coefficients and so on. This can still be done, I suppose, but it's more because of its defining property, as the splitting means not splitting, but this polynomial really gives you the extension. Okay, and I don't know if this polynomial splits. I suppose it splits because all its roots are, yeah, it also splits, but we can think about that later. It also splits. So in fact, kx is the splitting field of this. Yeah. And kx is the splitting field of something because it's a Galois extension. Yeah, I mean, from all the things you can say that this actually splits. Yeah. You can say it directly and it splits in kx. That's okay. So anyways, we did some small things. We have some questions left. We have some more questions left, and we learned some things. Okay. So suppose this is how it is, right? So we'll stop here and maybe. So we have mostly done. Please try the other questions. Now we will not spend more time on this. We will move forward. Is that fine? So it's good that we got some mathematics done. So the plan is to meet next on Tuesday. Okay. And by that time, what I expect, so if you do this, then we will move fast. We will be able to do some maths, because if you really summarize what we did today, if you go back and summarize, you will see that not much. I mean, just thinking slightly more clearly and doing. But now we want to move forward. So what I will say is, you read this. Okay, maybe you cannot see the still see the thing. So I'm in the book. So I'll just say this and then we'll stop. So you can read the section. I will not discuss the theory of the section. You can read it. It's easy. Certain things, and it looks like a long section, but if you see the pattern in the arguments, they are really same more or less. So yeah, read the section, and then next time on Tuesday we can try the problems. Maybe we should plan to maybe do the first 5 problems in the next class on Tuesday. Is that fine? Okay. Oh yeah, you have your college. Okay, okay, yeah. So yeah, I did think of that. Uh, yeah, but next Saturday, right? Yeah. So then, yeah, tomorrow also we have a class, but the topic there would be different, maybe. So, yeah, yeah, tomorrow 8 p.m. Yeah, so this is, I'll send a mail, but tomorrow 8 p.m. we are meeting. But there we might go fast. Their topic might be different. So last time we did some things related to circle and topology and quotient, so on. But yeah, you should join. You should join and see if you like how arguments go. Then we will not do this. So what should we do? Srijani, you will be able to join on Tuesday if we Tuesday morning. Okay. So hmm. So Aryan, I mean, why don't you read it independently and try the five problems, right? And yeah, first five. In fact, reading the section itself will take might I don't know. So you read the section and you do the first five problems. Okay, we will be doing it in the class, but you should. I mean, you do it and you tell me if there is something which you want to discuss. It's fine, right? And the next time when things are more non-trivial, we'll meet you and we'll try to do the next five on next Saturday. Okay? Yeah, I think you'll do fine. Yeah. So this is. This and I also wanted to discuss the INMO paper, but let's see when that